a second.
We can hear
Okay.
you, but we can't see you.
Maybe a little red light up there so that the camera is on.
What red light?
That's what I'm saying.
Oh, here, we get a green light. Okay, looks like we're on the air, right?
Yep, we can see you now.
I'll assume we're on the air. Okay, welcome to STA4821, Stochastic Models for Computer Science. First thing is, there's a notice here that says that time is important here because these 1 hour and 20-minute classes can only go 1 hour and 15 minutes exactly because I have to be able to fit the lecture on a CD that doesn't have the same capacity as a videotape. So if we get cut off at the end, don't worry, we'll start again following lecture. Okay, so first of all, I have here the syllabus for the course. And so the first thing I got to tell you is where you can download this, and then I'll read some of it, and you can download it. Also, I have some homeworks, one of which I'll pass out, but you can also download it, but since I'm going to discuss it today, I'll pass it out. And then others which everything else in the future, you just download from the website. So first of all, here's the website. This is STA4821, and the website is, okay, so we're out of, I need better ink here. Thank you. Okay, so this is www.csu.fau.bob/tilde/courses/ and that's it. So when you go there, you can download everything. In fact, all the homeworks for the semester are on there. But I don't advise you to download and start working on them in advance. In fact, I wouldn't even look at them in advance because they look like they're a lot harder than they really are. So it can be depressing. So just look at them as they're assigned. Okay, so here is the syllabus, which you should download. And it starts out, it has the catalog description, which I don't have to read you. Then it has the instructor. That's me. You don't need to know anything about that, except office hours. So let me put up the office hours, which are not on the website. And they are Tuesday. Let's get one of these that works. Tuesday. High-tech stuff. Okay, let's try this one. Maybe I shouldn't mix them up. I got to keep them separate, and when I get one that works, use it. Okay, so office hours. That one doesn't work. Okay. Let's try this one. Better. Okay, Tuesday. 12:30 to 3:30, and 5:30 to 7, and Thursday 5:30 to 7. I have a class that meets from 4 to 5:20, so this is a good time for people who take that class right after that class, and this is between the two classes. So I'm supposed to be in my office always during those times, but occasionally I play hooky. So if you want to come to my office, the best thing to do, even though you can walk in any time, is just send me an email or give me a telephone call. In fact, a lot of times the questions can be handled by email or telephone call. So try that first. Also, we can make an appointment for other times if that's more convenient for you. But those are the official office hours. Now, the name of the course, maybe I should say something about that. This is called Stochastic Models for Computer Science. Stochastic. Seems that people have a lot of trouble with the word stochastic. So maybe one of the requirements, main requirements for the course, by the end of the course, you got to be able to pronounce the word stochastic. We got stochastic models for computer science. Now, stochastic is just a fancy word. It means random, or probabilistic, or statistical. So, random. Models means that this is really a physics course, in the sense that what we're going to do here is we're going to observe something about randomness, which is a physical phenomenon, and then we're going to try and describe it in an abstract mathematical way that simplifies things in some sense. That is, it tries to capture the essence and get rid of the unimportant detail. And the model is mathematical. That is, it's represented in terms of, just like in physics when you learn about forces and accelerations, you have a law like Newton's law, F equals ma, that kind of thing. So we make mathematical models of this physical phenomena, randomness. And in particular, then you take those models, and what you try and do is manipulate the models to be able to learn something about the reality. And if the model is chosen appropriately, then it's simple enough to manipulate, but complex enough, rich enough, so that it tells you something about the reality, and that's the point. So throughout the course, I want to keep emphasizing that we're talking about making models of actual randomness. And what we're going to do is develop a theory, and also there'll be homeworks which will be largely based on simulation, which of course is something we'll cover in the course. And simulation is using a computer to generate artificial experiments. And what we'll do is compare the results of the simulation with the theory. Of course, if everything works out right, if you do it right, they will agree, and that's largely the point of the course, to understand how the mathematics reflects the reality, how the reality is described by the mathematics. So, but in particular, at first we'll be discussing subjects that are of general interest in this topic, in this field, because we're really starting at the beginning here. This is the first course in a subject that could go on forever. And then when we start specializing a little bit, getting into a little bit deeper, I'll be emphasizing things that relate specifically to computer science. Actually, the title of the course really should be Stochastic Models for Computer Science and Computer Engineering. There's really no favoritism for computer science here. It's just that without that, the title is too long. So think of it as computer science and computer engineering. Now, the prerequisite for this course, it says, I'm reading from the syllabus now, it says MAC 2312, which is the second calculus course, especially the relationship between the derivative and the definite integral, which is the fundamental theorem of calculus. And you need the ability to evaluate integrals numerically using a calculator or other software. So homework number 0, which I'll talk about soon, is a review of the topics from calculus that you're supposed to know, and that'll handle this part, and that'll give you an idea as to whether or not you have the background required for the course. It turns out that many people who have taken calculus complain that they forgot it, which is probably true, but it seems to me that there's generally no difference between the people that forgot it and the people that is, people took it a long time ago and forgot it, or the people that took it a semester ago and forgot it. It seems that very often what you learn in the freshman calculus is not the essential piece, which is what we need for this course. So a lot of it will be reviewed here. So we'll get back to that. You'll see that. Then the textbook. There are 2 textbooks listed here. One is by Garamani, called Fundamentals of Probability, 2nd edition. And the other one is a reference by Ross. It's called Introduction to Probability and Statistics for Engineers and Scientists, the 2nd edition. And it says, copies of both books and their solutions manuals will be kept on reserve in the library. So as far as the first book goes, the Garamani book, that's the official textbook for the course, and that's probably worth buying. And I will use that, I won't follow that book very closely because, for one thing, it has much more material than we're able to handle. But it is a good reference, and the way I handle this is I lecture, and in the lectures, when I cover a topic, I mention where it is in the textbook. So if it's a theorem, I'll say what the theorem number is, what page it is, that kind of thing. So if you have a textbook, you can follow along. But if you can't afford to buy the book, and you have a choice, say, between buying a book and buying a calculator that'll evaluate integrals for you, in my opinion, you're better off buying a calculator, because once the course is over, you won't be interested in the book anymore. And a calculator is something, a scientific calculator, is something that everybody who has a degree in computer science or engineering should have. So if you don't already have one, and you can only buy one thing, I would buy the calculator. Also, the book is on reserve in the library, so you can always go to the library and take it out for a short period of time and copy anything you want, I guess, page at a time. Now, the other book by Ross is simply a reference. And the difference between them is that the Garamani book is only about probability, and the Ross book is about probability and statistics. And at this moment, you don't know what the difference between the two is, but there is a difference. And I cover statistics in this course toward the end. I don't think that Ross covers the probability as well as Garamani does. So for that reason, I adopt the Garamani book as the official textbook. And then when we get toward the end of the course, since there's only a few pages actually that are used out of the Ross book, then my advice is, unless you're rich, don't buy that book, just go to the library. As I say, it's on reserve there. Also on reserve is the solutions manual for both books. So both books have exercises. There are answers to some of the exercises in the back of the books, and then there are more detailed answers in the solutions manual. But I don't think you'll need that because, for the most part, I don't use the examples that are in the book. So if you want to use them, that's fine. But I don't necessarily recommend it. So I think you'll see what I mean as we go along. Also, although it doesn't say this in the syllabus, I like to keep everything informal. So don't be worried about asking questions. In fact, I encourage that. So if you have questions, ask them. The more interaction there is, I think, the better. Because if I just lecture, it goes a lot faster, and it's probably a lot less clear. So ask any questions, and no matter how stupid the question is, ask it. Because if you ask a really stupid question, everybody else in the class will be happy that you asked it, and they didn't have to ask it and look stupid, but everybody's worried about it not knowing exactly the same thing. So don't worry about asking questions. In fact, that's the purpose of having a classroom. Otherwise, we might as well just tell you to read the book, and that would be the end of it. Then it lists a bunch of topics here, which there's no point reading at this point, but later on in the course, you might want to go back and make sure that those topics have been covered, and you could see then if a specific topic is mentioned, you know that's one of the things that's important for the course. The objectives. Let me read the objectives. It says, to provide certain technical skills that are important in computer science and engineering applications, to provide a feeling and appreciation of statistical concepts and reasoning in everyday life, and to show in passing that the subject is interesting, enlightening, and sometimes surprising, to examine the relationship between theory, that's the mathematical model, and experiment, which is simulation. So later on, at the end of the course, there'll be a form that asks you to evaluate the course with respect to the objectives. So be thinking about it as you go along. Try and see, as we go along, where these objectives are being met. And if you think they're not being met, or you don't see how they're being met, then those are the kind of questions you should raise. Because from my point of view, this is what I want to do. Then it says, topics 1 through 9, these are the things that are listed above, provide the theoretical background for the application of probabilistic and statistical reasoning. Homework assignments compare theory and simulation. The last topic provides an in-depth discussion of the application of these concepts to a realistic engineering model. So we're going to build up to a final homework which is different from all of the others and which sort of summarizes everything. And which by the time we get to it, I hope makes sense and is interesting. It says, overall, the topics promote proficiency in mathematical and scientific principles relevant to computer science and engineering. Well, at least that's the hope, that's the intention. So, keep in mind as we go along that that's what I'm trying to do. Also, in particular, one of them says that I want to show that the subject is interesting, enlightening, and sometimes surprising. I know that this is a required course. If it weren't, the number of students in this room would be 0. Nobody ever wants to take this course. But actually, this is really very interesting if you don't get bowled over by it. So just sit back and relax and try and get as much of it out of it as you can. Try and enjoy it. And at the end of the course, you'll see there's another course I give. There are several other courses I give for which this is the prerequisite. And so if nobody would and those are electives. So of course, if nobody would take this course, certainly nobody's going to take those courses. But it turns out that there's always few people who take this course who want to learn more and take the more advanced course. So in a sense, that's my measure. If people want to take another course in this after having been dragged kicking and screaming into this course, then for me, that's a success. So I hope everybody signs up for the next course. Rules. There will be 2 exams, a midterm and a final. Exams will be in-class, open book. Homework will be assigned, but only specifically designated assignments will be graded. Students are allowed to consult to be defined in class on homework problems. Grades will be based on the exams and the graded homework. Okay, so one of the exams, the midterm, will be given prior to the drop date. So the purpose of that exam, although there's a grade associated with it, is primarily feedback for your purpose. So when you take that exam, then you have sufficient time. I give it with sufficient time so that I can get the grades back and discuss it in class. And then you use that as the basis for deciding whether you want to stay in the course or not. And the way you should look at that is that if you do poorly on the exam, that doesn't necessarily mean anything. The question is, why did you do poorly? People generally do poorly because, I'm not really sure why. Maybe because the subject is tricky, maybe because they're nervous. But if you do poorly, but you say, oh, I knew that, or how could I be so stupid, or that kind of thing, then stay in the course. The grade is not important there. It's only a very small part of the final grade. It counts like a homework. On the other hand, if you have no idea what I'm talking about on the midterm exam, then that's the time to drop the course. Most people don't drop. It's very unusual for people to drop. So again, I take that as a measure. If a lot of people drop, even though we get their money before they drop, still it's not good. So I'm not trying to get people out of the course. It says that students will be allowed to consult. Oh, well, let's go back to the homework, how the homeworks are counted and the grades are made up. The grades are based primarily on the final exam, but sort of a mixture between the final and the homeworks. At the beginning, there won't be many homeworks, but towards the second half of the course, the second 2/3, there'll be a steady stream of homeworks about once a week. And the homeworks are very important because they summarize what's going on in the class. And then the final exam will be based on those homeworks. So the homeworks are designed primarily for teaching, not for grading, but there is some grade associated. The exam, final exam, is solely for grading. So what counts really is what you know at the end of the course, not what you know at the beginning of the course. So if you do well on the final, that's going to be the primary determinant of the grade. On the other hand, there's a sort of a floor on things. The final is based on the homework. So if you really did the homeworks and you understand what you were doing, you should be able to do the final. If you do the homeworks and you don't do too well on the final, the homeworks will provide a floor. So doing the homeworks is not going to help you directly in terms of your final grade if it would be an A. Then you have to do well on the final exam. But if you're worried about a C, doing the homework is very important, because it's hard to get a grade lower than a C if in fact you've done the homeworks. For one reason, because the final exam is based on the homeworks, and for another, because even if you don't do well on the final, the fact that you've done the homeworks sort of puts a floor on it. So the homeworks are very important. Now it says that you can consult, but you're not supposed to copy. So consult means that you can talk among yourselves, you can work in groups, you can ask questions in class. In fact, for the most part, I do the homeworks on the board as part of the class, and all you have to do is fill in the details. But when it comes to actually running a program or actually writing things down, you're supposed to do that yourself. So it's legitimate for you to get together and talk about things and ask what the answer is, but it's not legitimate for somebody in the group to get up and write the answers on the board and then everybody in the group copy it and write down, hand in exactly the same thing. But I can't really tell, and as I say, the grades on the homeworks are not that important for the final. The grades are mostly for your benefit and somewhat to protect you on the downside for your grade. What you can't do is you can't copy. And I tend to give the same homeworks every semester. There's like a template. And the reason for that is that these homeworks are very carefully planned out. They're carefully selected. And so at least the intention is that they're not just exercises or busy work. What they're supposed to do is they're supposed to explain the concepts in the course. And so for that reason, it's okay to talk about them because they're primarily for teaching purposes. On the other hand, if you simply copy them, that's just worthless, and that just means that what you're trying to do is get a grade for nothing. So here's my point. What typically people do is they go back and they find the homeworks from someone who took the course in a previous semester, and then they hand in the same homework. Don't do that, because then you're going to get caught for sure, because every semester, even though I use the same template, I change parameter values and I change functions that are in there. So the concept is not changed, but the answers are changed. So if you hand in a homework that has runs the code from a previous semester and prints out the answers that don't agree with the theory, because you calculated theory from one semester and ran the code for another semester, or if you have the theory from a previous semester, if you give the answer that is exactly the answer for lambda equals 3, and I give you lambda is equal to 2, then I know that you copied. And so don't do that under any circumstances. That's bad. And my recommendation is don't even look at the old homeworks, because it's easy to fall into that trap. So forget that the old homeworks exist. Just worry about what's given in the class. And then this is kind of elaborated on here in this note. It says, in homework problems, all theory answers recorded in the summary table must be supported by calculation, and all simulation results recorded in the table. Table, by the way, is every homework has a table associated with it where you write down your answers, then you attach whatever calculations you made on other pages. And when I grade it, I look at the table first. So it says, all simulation results recorded in the table must be supported by actual code and output. It will be taken as evidence of cheating if any theory result recorded in the table does not correspond to the accompanying calculation. In other words, there's always people who calculate something and they get an answer, 0.8, and then they look at someone else's papers, they're handing it in, and they got 0.7, so they change the answer and write 0.7 in the table and 0.8 in the calculation. Bad, don't do that. It's better to make an honest mistake or simply leave something out and say you don't know how to do it. But if you copy somebody else's answer and I catch that, or make things up, people tend to do that too. They know that lots of times probabilities turn out to be a half, a third, or something like that. So what they'll do is they'll run the simulation, they'll get an answer like 0.558, and so they'll write down for the theory 1/2, even though they have no idea what they're doing, because they're just guessing. That's not good. So don't try and fool me. Just if you don't know it, just say so. It's not a big deal. And if you know it, well, That's good. Okay, so it says it will be taken as evidence of cheating if any theory result recorded in the table does not correspond to the accompanying calculation, or if the simulation code, its printed output, and the output values recorded in the table are not consistent, or if simulation code with incorrect parameter values from a previous semester is used. So basically, if you just do your own work and actually run any code, there's no problem. So that's my advice. Okay, are there any questions about the general rules or anything like that?
I had a
Okay.
question.
Okay, so you should all download this
She said she had a
question.
question.
The question?
On the screen.
Girl on the
Question.
screen. Okay, how do we handle this? This is my first time on the air.
Okay, the question I had was, how do we hand in the homeworks, especially for us up here? Do we email them to you, or is that explained on the website?
I have no idea. But probably the best thing is, since there's more than one of you, is put them all together in an envelope and send them by campus mail.
Okay. Also, you said that the exams were open book.
Oh, I
Are they
can't hear
also-
you.
You said the exams were open book. Are they also open note and open homework, or just the book?
Open everything.
Everything. Okay.
Okay, the objective is to try and see what people know and minimize anxiety and that kind of stuff. So, yeah. And in fact, when you study for the exam, one of the ways to study for an exam is to decide what notes you should bring in. And the difficulty, the danger is, don't think it's open book, so I don't have to study. I can just bring in the book and look it up at the time of the exam. Because, as a matter of fact, it's more of a psychological crutch. If you have to actually bring in notes and a book and use it, then you're already in trouble. You shouldn't have to use those things. And for the midterm, what I do is I give the sample exam as the previous exam for the previous semester. And the exams are all pretty much the same, even though that doesn't seem to help in terms of the grades, because everybody seems to get bad grades anyhow. But maybe this semester will be different. Does that answer your question?
Yes, it does. Thanks.
I guess that was a yes. I can't hear it. Yes.
Yes.
Okay. Any other questions? All right, the assignment, let's start off with the assignment. Read the preface and pages 1 through 21. So in Garamani, read. Preface and 1 through 21. This is in the book Garamani, Gharamani. And the preface is especially important. Students tend not to read the preface, but the preface is where the author tells you what he thinks the audience for the book is, what he thinks their objectives are, and their preparation. So that'll give you some idea. Now, there are two homeworks. The first one is homework 0, and it's called Mathematics Review. And it's worth 25 points. Have a copy of it here. And then there's homework 1. But homework 1 will be due first. Homework 0 is actually a review. It has nothing directly to do with the course. So you can download it and start looking at it, but don't worry about it until I start discussing it in class. And it's important because it focuses on the elements of calculus that you need, which is probably not what most of you think you need. There's no tricks here about using strange trigonometric identities to evaluate integrals and things like that. That's all meaningless. This has to do with the essential meaning of what is an integral, because we're going to be using integrals in probability, although evaluating integrals is simple. Once you set the integral up, the evaluation is straightforward, because all the functions that I'm integrating are simple things like constants or exponentials or linear stuff. So you don't have to know any tricks of integration. Now, when you download that, there's also a place where you can click where you can download graph paper. And for the first homework, for homework number 0, I want you to use the graph paper that's there so that everybody is then using exactly the same scale. And also then, of course, you can't use software to plot it for you. You have to plot things by hand. And at least in the first time you do it, that's important. And also it makes it easier for me to grade, because then all I have to do is find one that's right and then take every other one and just hold it up to the light like this. And if the two match, then they're both right. And if they don't match, then one of them's wrong. So I like to keep things easy for myself as well. Second homework, actually homework number 1, is called the birthday problem. And so that's what I'm going to start with. So let me pass this out, and then we'll start with this. So I need, let's see.
We had another question over here in PSL.
Question, yep.
You said for us to do campus mail for the
Can
homework.
you say it louder, or can I turn this thing louder? I can't hear you.
Okay, you said to do campus mail for our homework. Do you want us to postmark it on the day it's due, or have it be there to you by the day it's due?
The rules for you in terms of when things are due should be the same as for the course here. In other words, you shouldn't have to do things sooner in order to get them to me. So on the due date, that's when you put them in the envelope and send them to me. Actually, that's really not very important. The due date on homework, for the most part, is not a big deal. So what I do is I'm willing to accept things late, but I don't want to encourage you to hand things in late. So it's better late than never. So if you can't do a homework and get it in on time, don't assume that that's the end of it. Do it. Also, for the most part, I actually do the homework in class. So there's usually 1 or 2 pieces that I don't do in class that the students actually have to do. And if you hand in the homework late, and I've already discussed that part in class, then on the late homework, I won't give credit for that part. But otherwise, there's little penalty for handing in late. And I don't like to say what the penalty is, whether it's 1 point, 2 points. It depends on how late and the alignment of the stars and things like that. But basically, I'm flexible. Purpose of this course, as far as I'm concerned, is to teach the material. And if I had my way, I wouldn't even give exams. But I have to. Okay, any other questions about that? Okay, so let's look at the birthday problem. And this problem is very simple. The whole thing is just doing it. And so let's read it. Well, let me start out by, rather reading it, let me start out by looking at a version of it. The idea is that you have a bunch of people in a room, and you want to ask how likely it is that at least 2 people in the room have the same birthday. So obviously, the answer depends on how many people there are in the room. If there's 1 person, probability is 0, because of course, there's a question here? A copy of the...
Homework and do you have an okay?
That's all I've passed out so far. All right, so you have a bunch of people in a room, and if the number of people is small, then it's unlikely that 2 people have the same birthday. If the number of people is large, then it is likely. For example, if there are 366 people, then of necessity, at least 2 people must have the same birthday. So one way to ask the question is to say, how many people do you have to have in a room such that the probability is 50-50, that is 1/2, that at least 2 people will have the same birthday. Now, when you ask the question that way, that means that you imagine that the number of people in the room is fixed, and then you run the experiment of questioning all of them, and you see how often what fraction of rooms with that number of people will actually have at least 2 people with the same birthday. Now, another way of looking at it, which is the way I'm going to look at it, is to say that for the homework problem, instead of doing it that way, what we'll do is imagine that you question people one at a time. And you say, what's your birthday to person number 1? And you record it. Then you go to person number 2, person number 3. And you keep on questioning people until for the first time you get 2 people with the same birthday. And at that time, you count how many people there were. Did the first birthday occur with the 3rd person, the 50th person, the 80th person, or so on. And then you do this over and over again, and you calculate the average number of people that you question until you get a match. So in one case, what you do is you fix the sample size. You fix the room size, and you see whether or not there's a match in that room. In the other case, which is the one that I want to simulate, what you do is you question the people one at a time until you get a match, and you ask yourself, how many people did that take? Now, this is straightforward, and so what I want to do is there's several points here. I want to test your intuition. I want to get you going on how you do these kind of homework problems, because when I go through the code, you'll see that I use BASIC, and I'll get back to that in a moment. And also I want to point out, make some observations about the way averages work, because what we'll do is we'll calculate the average number of people that you question until you get a match. So first, let's look at the case where I'm going to fix the number of people in the room, and I'm going to ask for the probability that at least 2 people have the same birthday. So imagine if, for example, you work in an office and all the people in the office agree that whenever anybody has a birthday, everybody else in the office is going to treat that person to lunch. And then you ask yourself, how come it happens, or does it happen, that with a relatively small number of people in the room, you find that 2 people have the same birthday? Does that happen often? If it does, is that a coincidence? That's the kind of thing we want to investigate. Now, I'm talking about probabilities here, and you don't know what probability is yet, because that's what the course is about. But everybody has a intuitive idea about probabilities, so this is going to be enough to get this problem going. Okay, so here's the idea. So what I'll do here is I'm going to draw a graph. So on the horizontal axis, I'm going to plot n, which is the number of people in a room, and that number can be 1, 2, 3, 4, 5, and so forth, and it'll end up here at 366. Because once I get to 366 people, I know that at least 2 people must have the same birthday, because there are only 365 birthdays.
I don't think it should be 367. It could be a leap year as well.
Okay, that's a good point. Leap year. In fact, there are other things that we're going to ignore when we do this. And so that focuses back on this idea of a model. Because ask yourself, suppose that we included leap years. That would make the problem more complicated, but would it affect the answer any? Do you think it makes any difference whether we count that there are 365 possible birthdays or 366 possible birthdays? And the answer is, well, it makes some difference, but conceptually it makes no difference. And if you look at the numbers, they're only going to vary in the umpteenth decimal place. So one of the questions you want to ask yourself in this course when you make models, at least in reality, is have I included too much or not enough? You want to get the proper trade-off. So this is a good example of that. We could make the problem more realistic, and the cost would be that it would make it much more complicated, and the insight that we would get, additional insight, would be essentially nothing. So that's a good point. Okay, so I'm going to ignore leap years. I'm also going to ignore other things when we make the calculation, like I'm going to assume that every birthday is as likely to occur as every other birthday. That is, I assume that any person has a probability of 1 over 365 of having any particular one of the possible 365 dates as their birthday. But in reality, that's not true either. more people are born in some seasons and other seasons. I don't know what they are. I guess maybe take spring as the most romantic season and add 9 months, and so you're going to have more people born 9 months from spring than you're going to have in spring. Or maybe more people are born 9 months from the coldest day in the winter. I don't know. But in any event, I'm going to ignore all that because it doesn't seem like it should make any difference. Of course it might, but at least at this level, let's assume it doesn't. Okay, so we're going to start with 1, and we're going to go all the way to 366. And what we're going to do for each value of n, I want to calculate the probability, let me call it p sub n, which is the probability that at least 2 people have the same birthday if the number of people in a room is n. Now, probability represents a frequency. This is what we'll see later. It represents a frequency, or in other words, a fraction of experiments. So in this case, what I would do is I'd get a group of people like this classroom, and I would conduct the experiment. In this classroom, maybe we have 40 people, so I'd be sitting over here at 40, and I would conduct the experiment, and either I would have a match among those 40 or I wouldn't. And then I would do it again with another 40 people, and another 40 people, and so on. And the probability that I'm looking at would be the fraction of those classrooms that have matches. So if half of the classrooms have matches and half of them don't, that would be a probability of 50%. So it's also sort of a measure of likelihood. How likely is it that a room with this number of people has at least 2 people with the same birthday? So since we're talking about fraction, that means that the maximum possible value is 1. So when n is 1, the probability that at least 2 people will have the same birthday is obviously 0, because that can't occur. And when n is 366, the probability is 1, because that must occur. When n is 2 people in a room, then it's sort of intuitively obvious that the probability of a match is 1 over 365, because the first person has some birthday, and whatever it is, the chance that the second person's birthday happens to be exactly that 1 should be 1 chance out of the 365 possibilities. So the probability of 2 people having the same birthday, if there are only 2 people considered, should be 1 over 365. Tiny. And then for n is equal to 3, it's going to be a little bit bigger, and n equals 4, a little bit bigger, and so forth. So what you're going to get, if you were to connect these dots, is you're going to get a curve, which you know starts at 0 and ends at 1. The question, though, is what does the curve look like? I just drew a linear curve. But it could look like this. It could go like this. It could go like this. It can do anything except oscillate. So this curve means that the probability of having a match is high for a small number of people. This curve means that the probability of having a match is small for a large number of people. And this curve is sort of in the middle. This is just a linear interpolation. So if I were looking at the 50% point, right here, 0.5, then where a horizontal line from here intersects the curve, that would be the value I'm looking for. But for my purposes, instead of fixing a number of people, what I'm going to do is I'm going to question people until I get a match. And then I'm going to ask the question, on the average, how many people do I have to question? So you might make the argument, reasonable argument, to say, well, let's see. First, I'll guess where the 50% point is. And if that projects over to here, then roughly that should be the average. If it projects over to here, then that should be the average. In other words, if the 50% point is, let's say, at 85 people, then you would expect that on the average, I'd have to question roughly 85 people, because half the time I'd question more, half the time I'd question less. So it's not exactly the same thing, but we're trying to develop some intuition here. So that's one way of looking at it. So what I'm going to do is I'm going to now imagine that we're going to question people one at a time and ask, on average, how many people do you think I have to question until I find my first match? And what I want you to do is look at this handout here, and you'll see that above the table, it says, before running the simulation, estimate the long-run average here. So in other words, I want you to guess, use your best judgment as to how many people on average you think you have to question until you find two people with the same birthday and write that number down. Now later on, we're going to find out exactly what that number is in theory, and we'll compare that with what you're going to actually get when you run this simulation. So the first thing I'm doing is going to test your intuition. And you should do that. Be honest. I mean, it doesn't matter. There is a right answer, of course. The right answer is exactly the theory answer. And of course, there's always somebody, if the theory answer is 85.72, there's always someone who guessed 85.72. I know you didn't really guess that. So make this guess a round number. Do you think it's 10 people, 20, 30, 50, 80? A typical answer is, I'm not necessarily promoting it or arguing against it. The typical answer is, well, let's see. We have a curve that's going to start here, end here. So this is roughly 180 right in the middle. So therefore, maybe 180 would be the answer. But maybe 180 seems a little bit big, so maybe it's half of that. On the other hand, maybe it seems small, so maybe it's more than that. So write down your answer, and then you'll see how good your intuition was. Okay, now here's the idea, the way in which we're going to answer the question. What I'm going to do is I'm going to imagine that I have my computer can generate random numbers which lie between 0 and 1. So this will turn out to be a very important point that we'll see later, but now just take my word for it that the random number generator, there is something called a random number generator, and what it does is the following. It's just as if you had a child's game with some kind of spinner. And the spinner, you flick it, and it picks out a number between 0 and 1. And all numbers between 0 and 1 are equally likely, whatever that means. In other words, there's no tendency for the spinner to lie one place as opposed to another place. So when I ask the computer to generate a random number, what it does in concept is it flicks this thing and then gets a value. And then I'm going to argue like this. I'm going to say, okay, let's look at person number 2. Now, person number 1 has some birthday, so I'm going to mark off a value here. This isn't to scale, but it's the best I can do, of 1 over 365. And then I'm going to spin the dial. And if the number that this dial gives me lies between 0 and 1 over 365, which it will with probability 1 over 365, then I will say that the second person's birthday is the same as the first person's. And if not, then I'll spin the dial again. But when I spin the dial again, I'm now going to compare its value with 2 over 365. Because if the second person's birthday does not match the first, that means now I have 2 separate birthdays. So the probability that the third person's birthday is one of those first 2 should be 2 chances out of 365. If the random number generator does not give me a value that lies in there, then I increase the interval to 3 over 365, and I spin it again. So each time I do it, the size of the interval gets larger because I have more and more people that in this pool that haven't matched, and eventually I'll get over here to 366. That is, when I question person number 366, if no matches occurred, a match must occur, and so this thing then will necessarily stop. Okay, so I'm going to write some code in BASIC which is going to do this for me, and then keep records of what happens. Now, let me write the code. You have it right in front of you, so all you have to do is run it, but that's a question in itself. So any questions about the strategy here? Does everybody believe that this strategy will work? So all that I'm assuming is that every time I spin the dial, that the probability that the dial will give me a value that lies in a certain interval is equal to the ratio of the length of that interval to the total interval. And since the total interval is of length 1, that means that the probability that the arrow will lie in an interval is equal to the length of that interval. In this case, the way I've drawn it here, 3 over 365. Okay, that corresponds to the birthdays, and we're assuming that the random number generator and the birthdays are in some sense equivalent. Okay, so now I want to run this experiment and see what happens. Okay, so let me write down the code here. It's in BASIC. Let me say something about BASIC. BASIC is a child's language. Kids learn this in junior high school, I think. BASIC was designed in the old days to be logically equivalent to Fortran, which was the major computer language. And Fortran was actually used for scientific computation, and BASIC was used as a way of teaching programming without having to worry about all of the syntax difficulties, all the rules that came about with Fortran. So it's a simplified child's version of Fortran. And this is sort of a secret that in a computer science course we're actually using BASIC. So my reputation could go down the dumper if anybody finds out about this. So this is not to go farther than this classroom or the TV broadcast. Anyhow, BASIC, it turns out, is ideal for this kind of course because the problems that the programs we're going to write here are only going to be 5, 6, 10 instructions at the most, and it's very easy to read. So it makes good pseudocode. So your choice is you can take the code that I give you where the logic is clear and you can rewrite it in some other language. There's a benefit to that because it shows you have to understand it rather than just using what I gave you. But there's a disadvantage, which is that sometimes people make mistakes and it becomes a programming problem, which has nothing to do with the course. And so don't fall into that trap. My advice is download BASIC someplace. I can tell you a little bit about that. If you send me an email, I can give you some advice as to how to get it. But in any event, you're all computer scientists and computer engineers. So my advice is download BASIC and learn it. It takes a minute if you're a computer scientist. And it's for the problems that we'll do in the future, and maybe for other problems that you will do, it turns out to be much more convenient, much better, and even more accurate in some cases than more sophisticated languages. Of course, it has the dreaded do loop in it, so that's why we can never mention that we actually use it. Okay, so here is my idea. The way BASIC works is that you number the instructions, and it doesn't matter what the numbers are except that they're in order, and then you refer to the instructions by number. So the first thing I'm going to do is define a counter called J, and I'm going to start with J equals 1. And in BASIC, everything defaults to 0, and you don't have to define a floating point versus fixed or anything like that. Everything is taken care of for you. So it'll become clear once I write this. I'll go back over this to what these things stand for. The next statement, statement number 110, is a counter n. N is equal to n plus 1. So what happens when this instruction is executed is initially n is taken to be 0, and then every time it's executed it simply increments the value n by 1. So it's a counter. Okay, here's the key instruction. Instruction number 120. If RND is greater than n divided by 365, then go to 110. Now, RND, this stands for random, and in BASIC, what this does is this calls up the random number generator, and in effect, it spins this dial. So whenever this RND is encountered, then a number between 0 and 1, which corresponds to spinning that dial, is returned by the computer. It's a random number. And what it does in this case is it compares that with n over 365. N is going to be the number of people questioned. So for example, when n is equal to 1, then I'm going to ask whether the random number is greater than 1 over 365. So for example, let's go back to here. Initially, n is equal to 1. That is, first time when I start it, this is going to be a 0, so n is going to be equal to 1. And I'm going to make a comparison with the random number and 1 over 365. If that random number is greater than that, that means that the second person's birthday did not match the first, because it didn't lie in here, it lies over here. So I want to question the next person. So I'll go to the next statement 110, I will increment n, so it's now 2, and I will drop down to this instruction again. This will generate a new random number. It'll compare that to 2 over 365. If it's less than that, that means that the third person matched one of the first two. And if it's greater than that, the third person's birthday is different. So I go back up to 110, I increment n, that is, I'm going to question the next person, and I keep doing that until for the first time this condition is not met, which means I have a match, and then I drop down and I simply do some bookkeeping. So statement number 130 defines a value m, which is going to be the previous value of m plus n plus 1. So what this is going to do now is it's going to accumulate the number of people that I questioned. Because when I drop down from here to here, that means that the number of people questioned is n plus 1. So if I questioned n plus 1 people, and I'm going to do this over and over again so I can calculate an average, that means that I have to sum the total number of people questioned, so I can divide that by the number of times I conducted the experiment. That will give me the average. Okay, so this accumulates the total number of people questioned. I'm almost done. What I want to do is I want to print the value of j. That's my counter. We'll get to that in a moment. I want to print the value of n plus 1. That's the number of people that I just questioned until I got my first match. And I want to print m over j, which is the average number of people questioned. I'll go back over this in a minute and write down what j, n, and m mean. Okay, statement number 150, I want to set n back to 0. And 160, I want to increment j by 1. And then 170, I want to go back to 110. And that's it. Okay, so let me go back over that. First of all, notice that as it's written, it's in an infinite loop. Because it goes to 110, it'll just keep on going through this over and over again. So I want you to, it says, here's the instructions. It says, adapt and run the following simulation. It is written in BASIC, but you may use any language you like. Fill in the table. I'll write the table on the board in a moment. You have it in front of you. Attach a printout of your code and output, and print only the values indicated in the table. Okay, so let's look at the table. Any questions about this before I erase it? Okay, I can redraw it if necessary. Okay, so here's your table. There's the experiment number. So this experiment 1, 2, 3, and so on, 4, 5, 10, 25, and like so on. Then we get to 1,000, and then 10,000. So this is going to be the J, and I'm going to do this 10,000 times. But I don't want you to print out the answers for all 10,000 of them. I just want you to print out the answers for experiment 1, 2, 3, and only the ones that are indicated here. So that means that you have to take this code and you have to change it so that, first of all, it doesn't loop an infinite number of times, it only does it 10,000 times. Of course, that when you actually run it, that just takes an instant. And second of all, you want to change the print statement so it prints out only for the values of j indicated and not for all 10,000 of them. So that's no big deal, but this is a characteristic of these kind of problems. I always give you the code, and then I ask you to make minor changes. So that means you can't simply copy the code directly and run it. You have to have some understanding of what you're doing before you run it. But this is simple. Okay, see what you're going to do is you're going to run this experiment 10,000 times. And then it's going to ask you for the number question this experiment. Number. I'll write just number now. And then it's going to ask you for the average. Okay, so the J is going to count the experiment number. So J is going to run from 1 to 10,000. Every time I run an experiment, I'm going to increment n the number of people questioned, and I'm going to accumulate that, and then I'm going to print the value of J. So the first time I go through this loop, it's going to print a 1. Then I'm going to print the value of n plus 1. That's the number of people questioned. Then I'm going to print the average, which the first time will be exactly the same. Then I set the n back to 0. I increment my, that's the number of people questioned, this experiment. I increment my j, which is the experiment number, and then I go back and I do it again. Okay. Excuse me? Okay, m is going to be the cumulative number of people questioned. So let me go through it. Suppose we did this. And let's suppose that the first time I run through the experiment, when j is equal to 1, the number of people that I questioned before I drop from here to here, that number is, let's say, 30. Okay, I'm making this up. So this means that the first time I conducted the experiment, I got a match on the 30th person. Then I take the cumulative number of people questioned so far, which is, in this case, is 30, and I divide it by the number of times I did the experiment, which in this case is 1. So this value would be 30. Or in other words, it would be 30 over 1. Okay, now I set n back to 0. I do experiment number 2. I go to 110, which sets n equal to 1. I spin my dial to see whether I've got a match. I keep on doing that until I get a match. And then if I get a match on the nth question, that means I've questioned n plus 1 people. So I take that n plus 1 and I add that in, so my new m is now the number I questioned the first time plus the number I questioned the second time. So let's say that the number questioned the second time is 40. So if I got a match on the 40th person, then the value of m would be 40 plus 30. So the average would be 40, look like this. It would be 30 plus the 40 divided by 2, which is 35. Then I do it again. Let's say the third time, the number of people questioned is 51. Then the average would be 30 plus 40 plus 51 divided by 3, whatever that turns out to be, and I would get some number. Okay, so the value of n is the number of people, actually n plus 1 will be the number of people questioned during this particular experiment. The value of j is which experiment I'm talking about. And since m is the cumulative number of people questioned in all experiments, and j is the number of experiments, m over j is the average number of people questioned per experiment. So what's going to happen is that these numbers are going to bounce all over the place because each one is an independent trial. So this number could be 86. This number could be 2. That's possible. This number could be 106, and so on. But these numbers are going to stabilize. That is, what you're going to see is that the average value is going to approach some value, some number, and then when I get to 100, it's not going to be much different from 1,000, or I should say it this way. 1,000 isn't going to be much different from 100, and 10,000 isn't going to be much different from 1,000. Everybody, of course, knows that. That's why averages are important. They tend to stabilize, and as long as the sample size is large enough, then they give a stable value. And so you could run this thing forever, and the values would never change very much, and in theory, they would approach a specific limit called the expected value, which is something that we're going to calculate later on in the course. So when you get down to here, whatever that value is, that's the average. And what you want to do is you want to compare that with the value that you wrote down where it says before running the simulation, estimate the long-run average here. Okay, so you can see this is very simple. You can see that there's some depth in this because I'm illustrating the idea of the stability of averages. Also, the random number generator will turn out to be very important. Right now, we're just assuming that it works, and we're using it only for something that's very simple. The logic is easy to follow, and you could see that if you knew BASIC, it would be easier to do it this way than it would be to write it in some other language. My opinion is that the overhead in learning BASIC is worth it for the rest of the course, in fact, for the rest of your life, because it's like having a really neat, easy calculator. But you don't have to. So it's up to you because, as I say, this is not a programming course. So as far as I'm concerned, the programming aspect of it is simply a tool. I assume you can write programs just like you can do arithmetic or other things that presumably you've learned in the past. Okay, so any questions about this? So it's easy to do. I mean, you just do it. There's no theory involved. The only thing is to learn how to do it and print out the results. And remember what you're supposed to do, this will be true in every homework, is you fill in a table and then you attach your actual printout of the code and the actual printout of the numbers, the simulation results. And just clip them to the together, staple in the upper left-hand corner. Don't scrunch things up, make life as easy for me as possible. Use 8.5 by 11 paper. There's always some people who use like little postage stamp paper. I don't know how they do that.
Excuse me. When I can use different programs, look like LabVIEW or STA4821.
Any language.
Yeah, when they bring out bring hole inside the program, I can give to you that.
I don't care. Any language. All I care about is to have attached to the cover sheet stuff that tells me you actually did it, so I can see that you ran the program, and also have the answers that you got from running the program listed in your table. And in this particular case, you're also supposed to have your estimate. And of course, the estimate should be approximately the value that you're going to get here. Well, it will be if you have good intuition. And so the question is, how many people on average do you think you would have to question? So we can make a little test. Because remember I said that one way, this is obviously the way to do it if you want to illustrate things using the computer. But another way to do it here is to say, well, we have a group of people, so why don't we just go through the people in this class and see whether or not we have a match. Of course, that's only one trial, but if we have a match in this classroom and there's maybe, 40 people here, then that would indicate that if we have a match, then that would indicate that the number that you would expect to question on average would be relatively low, or we were just very unlucky in that we happen to get a match with a small number. On the other hand, if we don't get a match, that would indicate that maybe the average number of people you should question should be large. So let's run this simple experiment and see whether or not we have at least 2 people in the room with the same birthday. Okay. So when you hear a birthday, we don't have to go all the way around. If it happens, just say we have a match and that'll end it. Okay, my birthday is March 12th. Anybody have a birthday March 12th? Your birthday is March 12th? Case closed.
I'm just kidding.
Oh, you don't have a birthday March 12th? All right, your birthday.
June 21st.
Anybody have March 12th or June 21st? Your birthday.
March 19th.
Wait, let me go down the line here. September 15th. September 5th. February 11th.
March 19th.
March 19th. September 23rd.
7th August.
7th August.
July 2nd.
July 2nd.
December 2nd.
December 2nd.
10th April.
April 10th.
August 19th.
August 19th.
August 18th.
August 18th. We got a match? Okay. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14, 20, 25, 30. We got 33 people in the room, and we had a match. So the question is, did we see something unusual there, or would you expect to get a match with 32 people in the room? Anybody have an answer to that? What do you think the answer is here? Anybody want to give me an answer and a reason for, yeah?
About 30 probably.
You think the average is about 30? Anybody else?
About 75?
What was that?
75?
75, okay. Big difference there. Any others? Yeah.
45.
What do you got?
45.
25.
45.
45, okay.
Maybe, I mean, it would fluctuate, I guess, depending upon the population. Like if you're taking the population, like generally people like born in winter, for example, the answer would be different over there. Don't you think?
Well, we're saying that this is what our model has. Built into it, when I use this random number generator and this statement right here, what I'm assuming is that every birthday is as likely as every other birthday. So in other words, when I question an individual selected at random, the probability that his birthday is January 1st is 1 over 365. Probability that January 2nd is 1 over 365. Now, that may not be exactly right, but it's probably pretty close. And if the true probabilities are close to that, then you would expect that the average number I questioned would not be much different. It should not be very sensitive. But this is my intuition. It should not be very sensitive to those things. Well, it turns out that when you run the program, you'll find out that the answer turns out to be roughly 24 or so. And we'll see later that the answer is going to lie, it's going to lie exactly, I'll give you the exact answer, someplace between 24 and 25. So most people find this very surprising. And if you've seen it before, of course, it's not surprising. But if you've never thought about this before, and you guess what most people guess, typical guess is an answer around 180 or so. That is 365 over 2. And that's way off. So we'll analyze this later in the course. But if your intuition is way off, take that as a warning, or maybe not a warning, an insight. The strange thing about this course is that most people come into this with a preconceived notion about the way life really works, and as you'll see when we go through this, most people's intuition is completely backwards, and life is exactly the opposite of what you think, which of course would probably explain a lot of the difficulties you've already gone through in life. Okay, so we have 29 seconds left, and that's it, I guess. Yes?
What do next class?
Let's make this do a week and a half so you have time to ask questions in class. Because this is just a matter of doing it. There's no theory involved.